Hi everyone. In this video, we are going to discuss about a very interesting topic in geometry called locus. Now, what is locus? Well, the formal definition of locus is kind of like this. It says that the locus is the path traced by a point moving under some geometric conditions. So essentially, this is nothing but the path of a point that is moving under certain conditions, right? We're going to take a few examples to understand this concept here. And I think the easiest one to visualize and understand would be a circle. We're going to see how the circle is nothing but the locus of a moving point under a certain condition. So here we are going to take a moving point which is moving in such a way that it always maintains a fixed distance from a fixed point, right? So there are 2 points involved. There is one point is a fixed point and another one is a moving point, and the moving point is always at a fixed distance from the fixed point. So let's look at a diagram here. So here I have tried to show the path of a moving point which is always maintaining a distance of r unit from the fixed point O. Let's say this is the fixed point O right here. Now if the moving point, let's suppose the point is somewhere here, the point P. So that point is actually moving, but it always maintains a distance of r unit from the fixed point O. And as you can imagine, the path of this moving point is essentially going to look like a circle. So if I take a few more dots on this path, meaning if I take a few more points on this path, then it's kind of going to look like this. So this is exactly looking like a circle. Now how many points we have on this circle? Well, there are infinite number of points because a point is such a tiny little thing that only has a position but it does not have any dimension. So then if we look at the definition of a circle, that can be described like this. A circle is nothing but the locus of a moving point that maintains a fixed distance from a fixed point. So there are two interesting things here. There is a fixed distance and a fixed point. And actually the fixed point is called the center of the circle, where I have this pink dot at the center of the circle, in the middle of the circle. So let me name it as O. So let's call it as O. And this O is the fixed point, which is nothing but the center of the circle. And the fixed distance that we are talking about, this fixed distance is nothing but the radius of the circle. That is from the center up to the circumference, that distance is nothing but the radius. And here I have denoted that with a lowercase r, so that is the radius, and the fixed point O is the center of the circle, right? And also from this definition, we can quickly derive the equation of a circle. It's kind of like this. If you think about the location of the moving point P right here, let's suppose that the P is at a position x, y. Since P's position is variable because P is a moving point, it's moving, I'm going to use x, y as the coordinates of this moving point P, and then it is always at a fixed distance of r units from the fixed point O, and O must also have a location. Let's assume that O's location is h, k. Then from the distance formula, can we say it like this? Well, this distance r would be equal to square root of x minus h whole squared plus y minus k whole squared. This is the distance formula that I'm using here. Now if we square both sides of this equation, then we get something like this. R squared is equal to x minus h whole squared plus y minus k whole squared, and that is the equation of a circle. That's the general form of the equation of a circle. We'll discuss about it in more details when we start our series on circle as a conic section. But here I just wanted to quickly show you that from this definition we can easily derive the equation of a circle, which is r squared equals x minus h whole squared plus y minus k whole squared. Or you can write it the other way also. You can call it as x minus h whole squared plus y minus k whole squared equals r squared, where h, k would be the location of the center of the circle and r is the radius of the circle. Let's look at another example where the locus is also a circle. For example, let's suppose we have a moving point P which is moving in such a way that it is always at the right angle from two fixed points A and B. That means the line segment AP and BP, they are always at right angle, meaning they are perpendicular to each other. AP and BP, they are perpendicular to each other, and P is moving in that style. So wherever P is, AP and BP, they are perpendicular to each other, and that kind of a point will also trace a path which will look like a circle, because we know that the diameter of a circle always creates a 90-degree angle on anywhere on the circumference. So if P is moving in such a way that AP and BP are always perpendicular, that means we are talking about AB as the diameter of a circle. circle and P must be on the circumference of that circle. So the path of P will also look like a circle. Next, let's talk about concentric circles and see what kind of locus is that. Here, let's assume that we have a point P which is always maintaining a certain distance or a fixed distance from the center of an existing circle. The existing circle is the one in white color, and from the center of the white circle, point P always maintains a fixed distance. And if P is moving in that fashion, then how would the path of this moving point P look like? Well, it is going to look like something like the dotted circle that I have here. The circle may be outside of the white circle or inside of the white circle, depending on how much distance that P is maintaining from the center of the existing white circle. So if the distance is less than the radius of the white circle, then obviously P's locus will be inside the white circle, and if distance of P from the center of the white circle is larger than the radius of the white circle, then obviously the locus of P would look like a circle outside of the white circle. So now, as you can imagine, that if I take a bunch more points on this locus and if I fill in all those gaps with all tiny little points there, right? So it's like, you are going to put infinite number of points on this path, then this path is going to look like a circle like this. So that is how concentric circles are created. A concentric circle is also the locus of a moving point which is maintaining a fixed distance from the center of an existing circle. I hope it made sense so far. Next, we are going to look at another interesting locus which is called the perpendicular bisector. So let's have a look. Here we are going to talk about the locus of a moving point which is always at equal distance from two fixed points. So let's first take the two fixed points like this. Let's say the fixed points are point A and B. And then we are talking about another point which is the moving point that maintains equal distance from these two fixed points. So now I'm going to plot the moving point in pink color. Let's assume that the point is P. So that's a point P, for example. Now this point is always maintaining equal distance from the two fixed points. That means these two distances right here. So let me quickly draw it. So this distance right here. So from P to the point A and then from P to the point B, these two distances are equal. That means the line segment AP and line segment PB or BP, they are actually of equal length. And obviously P would be the midpoint on the line segment AB. So now if you think about it, this point is moving in such a way that it always maintains equal distance from A and B, which are the two given fixed points, right? Now let's see what could be another location of P. Well, now I'm going to draw another location of P. Let's suppose here is another position of P and then another position of P and then another position of P. And similarly, we could have a few positions below the line AB. Say for example, here could be one position, here could be another position of P. I'm just taking a few discrete positions of P, right? Now, if P is maintaining equal distance from A and B, then if P now is at a position which is just above the line there, right? Say this position is now P sub 1. So now I'm going to call this position as P sub 1. And then the other location, suppose we call it as P sub 2. And then maybe the other one as P sub 3. Right? So I have three different locations there. Now for each of these positions, P is equally distanced from A and B. That means if we join the points A and P sub 1 and similarly P sub 1 and B, these two line segments will also be of equal length. So let me indicate that. So this will be equal to this line segment right here. So that would be A P sub 1 will be equal to P sub 1 B. Those two line segments will be equal. And similarly, if we join A with P sub 2 and B with P sub 2, then the line segment A P sub 2 and the line segment P sub 2B, they will also be of equal length because P is always at equal distance from A and B. So then these two line segments right here, now I am indicating with red color. So these two line segments will also be of equal length. And similarly, if we join A with P sub 3, the two line segments A P sub 3 and P sub 3B, they will also be of equal length. And now I am going to join all these positions and see how that looks like. And as you can see, all those positions of the moving point P is looking like a straight line. Now this straight line also has another interesting property here, that yes, of course it is a straight line, and also it is actually bisecting the line segment AB, and it is perpendicular to AB. We are going to prove that now. This straight line, which is nothing but the locus of the moving point P, this straight line is perpendicular to the line segment AB, and it equally divides the line segment AB. So how are we going to prove it? Well, now let's consider the triangle A, B and P sub 3. Right, so I am now considering the triangle A, B and P sub 3. This triangle is divided into two triangles, and the two triangles are like this. One is AP, P sub 3, and the other triangle would be P, B and P sub 3. Now let's try to understand what's going on with these two triangles, right? So for these two triangles, can we say something like this? We know that AP and PB, they are of equal length, because P is the moving point that maintains equal distance from A and B. So anywhere on this line, P's distance from A and B, they are equal. So then AP equals PB, can we write it like this? And similarly, we can also say that AP sub 3 is also equal to the line segment P sub 3B. And then if you consider the line segment P sub 3, that is common side for both the triangles. So now for these two triangles, we can clearly see that their corresponding sides are of equal length. That means using the SSS criteria of congruence, we can say that these two triangles are congruent. So let me quickly make a note here that the triangle APP sub 3 and the triangle PBP sub 3, they are actually congruent. Now since they are congruent, then obviously their corresponding angles also will be of equal size. Then we can say that angle APP sub 3 is definitely equal to BPP sub 3. Now if you think about it, the sum of these two angles is a straight angle because they are right there at the point P on one side of the line segment AB. So their sum is 180 degrees. So we can write it as, and let's assume that each of those angles are equal to some alpha. I'm just using a variable alpha. So let's assume that they are equal to alpha. Now we can say that 2 times alpha, because each of them is equal to alpha as per our assumption. So 2 times alpha is equal to 180 degree, and clearly alpha would be equal to 90 degree. So we have been able to prove that the straight line P sub 3, which is nothing but the locus of our moving point P, that straight line is actually perpendicular to the line segment AB, and that is why this straight line, the new pink straight line, which is the locus of the moving point P, is called the perpendicular bisector of the line segment AB, where A and B are two fixed points and P maintains equal distance from both A and B. I hope the concept of perpendicular bisector is clear now. Next, we are going to talk about another interesting locus which acts like an angle bisector between two lines. So let me first draw the diagram. Here in the diagram, I have two intersecting straight lines, straight line A and straight line B. They intersect each other at point O. And now we have a point P, that's a moving point P of course, and the point P is moving in such a way that it always maintains equal distance from these two lines. So now we can say that the perpendicular distance from P to the line A, that is PR, is equal to the perpendicular distance from P to the line B, that is PQ. And because P is moving in such a way that it always maintains equal distance from the two given intersecting lines, then we can say that PR would be equal to PQ. And obviously the angle PRO and the angle PQO, they are 90 degree angle because we are talking about perpendicular distance of P from the straight lines, right? So clearly the two triangles OQP and ORP, those two triangles are right triangles and their hypotenuse is common, and their one side, which is RP and QP, those two sides are of equal length because P maintains equal distance from the two lines A and B. So for these two right triangles, then we have hypotenuse as common and the other side is of equal length. Then obviously the third side will also be of equal length since they are right triangle, and then clearly those two triangles are congruent triangles. So we can say that triangle OQP is congruent to the triangle ORP, I have already created a separate video on triangle congruence. I have shared the link in the description. Feel free to watch that video. Now, since both the triangles are congruent, then their corresponding angles will also be of equal size. Then we can say that the angle ROP will be equal to the angle QOP, and that's exactly what we wanted to prove, that the locus of the moving point P, which is nothing but a straight line, and that straight line bisects the angle between the two original straight lines A and B. So if there is a point that always maintains an equal distance from two intersecting lines, then obviously the locus of that point is going to look like an angle bisector. And also, if you want to say it the other way, the angle bisector of two intersecting lines is nothing but the locus of a moving point which maintains equal distance from the two lines. I hope the concept of angle bisector is clear now. Next, we are going to talk about straight line. So the topic of discussion here is what kind of a locus is a straight line. Meaning a straight line is probably the locus of some sort of a moving point, and let's try to find out what kind of a locus is that. The original definition of a straight line is kind of like this. It is actually the locus of a moving point that moves in a particular direction and in the exact opposite direction. So if a point moves in one particular direction and then it moves exactly in the opposite direction all the way to infinity, then that creates a straight line. So if we imagine a point P that moves in one particular direction, that means it's kind of moving like this in this direction, and then from there again it moves in the same direction, again it moves in the same direction, and again it moves in the same direction. It keeps on moving like this, right? And then you can imagine like what kind of path that it is going to trace. Well, actually it is going to trace a path which is going to look like a straight line. And also the point can move in the exact opposite direction. For example, if the point also moves in this direction, then this entire path will look like a straight line. And that is why if you take any 2 points on a straight line, the slope between those 2 points will be equal to the slope of the line segment between any 2 points on the straight line. Say for example, if we have a straight line like this, now I'm going to take a straight line here, and on this blue line, if we take 2 points, let's say suppose I'm taking a point right here, let's say we have a point A and point B, and also let's take another 2 points, let's say suppose point C and point D. So the slope of the line segment between any 2 points on the straight line, so we can say slope of AB is equal to slope of BC is also equal to the slope of CD, and so on. So that's a very interesting property of straight line, that a straight line is the locus of a moving point that moves in the same direction all the way to infinity, and also it moves in the opposite direction all the way to infinity, and that kind of a locus is actually a straight line. And the slope of the line segment between any 2 points on the straight line, that slope will be equal. All the line segments on this straight line will have equal slope. Next, we are going to talk about the locus of a moving point P as a line parallel to an existing line. Suppose we have a given line A, which is in blue color, and if you imagine a moving point P that moves in such a way that it always maintains a fixed distance from the given line A, then the locus of that point would be a parallel line on either side of the given line. If the point is moving on the upper side of this line, then it will be the dotted pink line on the upper side of the given line, and that dotted pink line will be parallel to the given line. Why? Because it maintains the same distance. We know from the definition of parallel lines that the distance between two parallel lines is constant everywhere, right? And similarly, if the moving point is moving on the lower side of the given line, then the dotted pink line on the lower side will be the path of this moving point, and there again it is maintaining same distance from the fixed line. So this dotted pink line will be a line parallel to the given line in blue color. So the main idea here is that a parallel line is always at the same distance or equal distance or fixed distance from a given line. Next, we are going to discuss about the diameter of a circle as a locus of a moving point. Here in the diagram we have a circle and we have two fixed points on the circle, point A and point B, and here we are talking about the locus of a moving point P, and the point is moving in such a way that it is always equidistant from both point A and point B. That means it is the perpendicular bisector of the line segment AB. We have already discussed this topic up above, that if a point moves in such a way that it always maintains the same distance from two fixed fixed points, then the locus of that point is nothing but a perpendicular bisector of the line segment joining the two fixed points. So in this case, we clearly know that this is going to be a perpendicular bisector. Alright, now if it is perpendicular bisector of the line segment AB, somehow we have to prove that this locus, the dotted pink line, is the diameter of the circle. So how are we going to prove it? Well, we have to do a couple of things here. From the properties of circle, we know that the diameter always subtends an angle of 90 degree on the circumference. So here, if we can somehow prove that the angle PAC or angle PBC is a 90 degree angle, then clearly we can say that PC, the locus of the moving point P, in this case we are going to focus on only the portion PC. So PC would be the diameter of this circle. So our task here is that we have to prove the angle PAC is a 90 degree angle. I'm now going to draw one additional line segment here. I joined the points A and O. Since the locus of the point P in this example is also a perpendicular bisector of the line segment AB, then these angles would be 90 degree angles right here. Let me highlight that. Also, I have assigned a variable for each of the angles there. I am using the lowercase letters there. So if you look at the triangle AOP, the angle OAP and the angle OPA, they are equal angle because it's an isosceles triangle, and I am calling that as a degree or a radian, right? And similarly, I am calling the angle OAB as angle lowercase b, and the angle BAC I am calling it as lowercase c, and the angle ACO I am calling it as lowercase d. So we have to prove that A plus B plus C is a 90 degree. If we can prove that, then PC will be the diameter of this circle, right? Now let's look at triangle ACR. I have named that point. It's the intersection of the locus and the line segment AB. I have named it as uppercase R. So if you look at triangle ACR, it's a right triangle obviously. And in that case, we can say that C plus D would be equal to 90 degree. And then if we look at the triangle ACO, or OAC, that is an isosceles triangle because OA equals OC, that's the radius of this circle. So then we can say that the angle OAC will be equal to the angle OCA, and from here we can say that B plus C is equal to D. And if we substitute the value of D in equation 1, then what are we going to get? We are going to get C plus, in place of D, I am going to write B plus C, and that is equal to 90 degree. And from here we can say that, well, this is actually B plus 2 times C is equal to 90 degree, and I am going to mark this as equation number 2. And also if we look at the triangle ARP, that is also a right triangle, and then the sum of the angles APR and the angle PAR, that would also be equal to 90 degree. And now what is angle APR? Well, angle APR is actually lowercase a, so I'm writing a here, plus what is angle PAR? Well, PAR is actually a plus b, so I'm writing again a plus b, and that is equal to 90 degree. And from here can we say that this is actually 2 times a plus b is equal to 90 degree, and let me mark it as equation number 3. And then if we add equation number 2 and 3, so now I'm going to do this quick little addition here. So equation number 2 and equation number 3, this is going to give us, on the left hand side we are going to get B plus 2 times C plus 2 times A plus B, and on the right hand side we are going to get 90 degree plus 90 degree. And from here we can clearly say that this is 2 times A plus 2 times B plus 2 times C. So this is actually 2 times A plus B plus C is equal to 180 degree, and from here we get A plus B plus C is equal to 180 degree over 2, that is equal to 90 degree. And that's exactly what we needed to prove. As you can see up there, I am underlining with a pink line there. We needed to prove that A plus B plus C equals 90 degree. Then we can clearly say that the locus of the moving point P in this diagram, it's actually the line segment PC. That's actually the locus of our moving point P. That locus is actually the diameter of this circle, because we know that the diameter of a circle subtends an angle of 90 degree on the circumference, and here we have been able to prove that A plus B plus C is equal to 90 degree. So our proof is pretty much complete. We can conclude that yes, the locus of this moving point P is the diameter of the circle, and P is moving by maintaining equal distance from the two fixed points on the circle. circle and the fixed points are A and B. I hope everything made sense. Thank you for watching. See you in the next video.